Welcome back. Today, we're diving deeper into the fascinating world of web crawlers and exploring some advanced features that can significantly enhance your scraping skills. So far, we've learned that web scraping involves building a web crawler using tools like Python, requests, and Beautiful Soup for fetching and parsing HTML. We also covered the importance of adhering to legal considerations, such as checking a website's robots.txt file and handling links appropriately. Additionally, we learned how to store scraped data in a CSV format for future use. As we progress, we'll continue to enhance our web crawling skills while maintaining responsible practices. Now, let's talk about some of the advanced features that will take your web scraping game to the next level. First up, we'll explore pagination, which allows you to navigate through multiple pages of data easily. We've all been there, right? Scraping just one page can only get you so far. Next, we'll look into managing cookies and sessions, a crucial step for maintaining login states. And let's not forget about using proxies to manage requests and prevent getting blocked, which can really help you scrape more efficiently. It's all about refining your tools to make your scraping arsenal more potent. So let's gear up and enhance those skills. You're going to love what's coming next. Now let's implement the following multi-threaded web scraping functionality. We begin by importing the necessary libraries: requests for making HTTP requests, Beautiful Soup from BS4 for parsing HTML, and Thread Pool Executor from concurrent.futures to handle the multi-threading part. Next, we define a function. Let's call it fetchPage. This function will take a URL as input and retrieve its HTML content. If the request is successful, indicated by a status code of 200, the function will return the page's HTML. If something goes awry, it'll print a message to indicate the failure and return none. Then, we move on to the parse titles function, which utilizes Beautiful Soup to extract titles from the page. Specifically, it's looking for H1 tags, compiling their text into a nice, tidy list. To scrape multiple pages, we set a base URL and generate a list of URLs using a list comprehension. Here's where it gets interesting. Using Thread Pool Executor, we can manage our workers. In this scenario, we'll have a maximum of 5 concurrent threads executing the fetchPage function across all the URLs we generated. Finally, we'll loop through the retrieved HTML pages, and, if they're available, we'll parse and extend our list of titles. Then we can print those titles out for review. This approach significantly enhances the efficiency of our web scraper. Now, let's implement a delay between our requests to ensure we scrape responsibly. The code begins by importing the time and random modules, which will help us introduce a random pause between each request. We define a new function called fetchPageWithDelay, which takes a URL as an argument. Inside this function, we call time.sleep with a random value generated by random.uniform13 to create a delay of 1 to 3 seconds before making the actual request. This delay is essential as it reduces the likelihood of overwhelming the website's server and helps us avoid potential IP bans. Next, we use a thread pool executor to manage our requests concurrently, just as we did in the previous example. However, instead of calling the fetchPage function directly, we now use fetchPageWithDelay. By implementing this adjustment, we maintain our efficient scraping process while adding a safeguard that reflects responsible scraping practices. As a result, this enhanced method allows us to gather data effectively without putting undue strain on the website we are scraping. Next, we're going to write some code to scrape JavaScript-rendered content using Selenium. First things first, let's import the necessary modules from Selenium, specifically the WebDriver and BY components. Now, we need to create an instance of the Chrome WebDriver, which is pretty cool because it lets us control the browser programmatically. Once we have our WebDriver set up, we'll tell the browser to navigate to our target page by using the GET method and passing in the URL we want to scrape. But wait, before we start scraping, we have to ensure that all the page elements are fully loaded. For this, we use the implicitly_wait method, setting a maximum wait time of 10 seconds. This step is super important for pages that rely heavily on JavaScript to render content, as it gives the elements the time they need to pop up. Now, to get the content we want, we can use the findElements method with by.tagname to grab all the h1 tags from the loaded page. This is how we collect the dynamically generated titles produced by the web page. Finally, we'll loop through the retrieved elements to print their text content, which will display the titles for us right there. And don't forget, once we finish our scraping, we must call driver.quit to properly close the browser and free up those resources. Now, let's dive into how we can implement automatic data extraction using the LXML library. So, we begin by importing the necessary modules, HTML from LXML and requests. The first thing we need to do is make an HTTP GET request to our target URL, which will fetch the web page content for us. After we get the response, we parse that HTML content using html.fromString. This creates a tree structure, allowing us to search for specific elements within our document precisely. Next up, we use XPath to grab the specific data we want from this parsed tree. We'll call the XPath function with an expression that selects all text contents within h1 tags, since those are commonly used for headings. So, by specifying the XPath expression wwh1/text, we make sure to pull out only the inner text content of each heading element. This level of targeting really streamlines our extraction process, especially when we're working with complex documents that might have nested elements or various similar tag types. Finally, we print out those extracted titles, which really shows off just how concise XPath can be for web scraping tasks. We start by creating a session using requests.session, which allows us to persist cookies and maintain a logged-in state throughout our requests. After that, we prepare a payload dictionary, where we replace the placeholders with our actual login credentials, specifically the username and password required by the target site. Next, we send a POST request to the login URL with our payload, effectively logging in and creating a session that retains those authentication cookies. Once we're authenticated, we can navigate to a URL that requires us to be logged in. This is done using a GET request to the protected page. To ensure our scraping is successful, we check for a status code of 200. That's the golden number, indicating that the page was retrieved correctly. If successful, we then initialize Beautiful Soup to parse the HTML content returned from the protected page. We search for all h1 tags on the page and extract their text, enabling us to gather the titles displayed there. But remember, if the request fails, we print an error message to keep things robust, ensuring that we're informed if something doesn't go as planned. Now, let's explore how to incorporate error handling into our web scraping logic. The fetch page function is designed to retrieve the HTML content from a specified URL, and it utilizes a try block to attempt the request. This is vital as it allows us to catch errors if they occur. By calling requests.getURL, we send a request to grab the web page. Now, if the request runs into an issue, like a 404 or 500 response, response.raiseForStatus will trigger an exception. This makes it super easy to identify HTTP errors without complicating things too much. In the accept block, we catch any exceptions that pop up from the request and display a helpful error message that details what went wrong. This step is crucial because it prevents our entire program from crashing due to a single fault, making our crawler much more robust. Returning none in case of an error allows us to handle the issue gracefully in the crawling workflow, which ensures that even if some pages fail to load, the rest of our scraping process can continue smoothly. Implementing such error handling practices can significantly strengthen the reliability of our web scraping applications. So there you have it. We've covered some advanced features of web crawlers that can really help you become more efficient and effective in your web scraping endeavors. We dove into multi-threading to speed up your requests, talked about adding delays to stay under the radar of website restrictions, and explored scraping JavaScript-loaded content with Selenium. Plus, we leveraged XPath for precise element extraction, tackled handling authentication, and implemented robust error handling. As you explore these concepts, really remember that ethical practices should always be at the forefront of your mind. The web is a vast and exciting place filled with data just waiting to be explored, but it's crucial to respect the resources provided by the sites you scrape. Now, go ahead, unleash those advanced techniques and empower your web crawlers to bring back the data you need. Happy scraping!